Hello everyone, this is Aditya and today we are going to do ordinary differential equation and we'll cover everything from basics to the advanced level, and of course it is for your engineering mathematics too. So get ready for diving into the ordinary differential equations, and now let's start with the lecture. But before that, please do like and subscribe my channel, and now let's dive into the topic. Okay, so before starting with the ordinary differential equations, you all must know that what is a differential equation. Well, a equation which consists of differential terms. What does it mean? For example, dy by dx plus x is equal to 0. It is a differential equation. d2y by dx square. Don't worry about this. We will discuss. Plus y dx by, dy by dx is equal to suppose 0. This is also a differential equation, right? So all such expressions which involve differentials or derivatives along with the independent or the dependent variables and somewhat like that is said to be a differential equation, right? And of course there can be n number of independent variables, right? So now let's see further. Okay, let me raise this. Okay, so what is ODE, this ordinary differential equation? Well, let's see. Okay, so basically ODE, it consists of only one different, one independent variable, right? Independent variable, right? What does it mean? For example, we can take simple d3y by dx cube plus dy by dx to the power 5 is equal to a some arbitrary constant to the power x. This is a ordinary differential equation, right? Okay. And if we see, suppose d2 v by dt square is equal to k, where k is a constant, del v by del x whole square. Of course, here should also be del, right? Partial derivative. Because here there are three variables, right? There are two independent variables in this case, right? So it is called a partial differential equation, right? I we are understanding this, okay? And we will be working upon the ordinary differential equations, right? And that too the linear differential equations of degree 1 and higher, right? Now, having said the word degree, what does it mean? Let's see. So basically, if I use the word degree, what does it mean? But before that, we should know the order, right? Suppose I wrote d2y by dx square plus dy by dx plus x is equal to suppose 0, right? I have written this. So what is the degree? Well, we won't discuss first of all degree, we will discuss the order. So order is the highest order derivative, right? For example, d2. So here 2 is the order, right? Okay. And degree is defined as the power to which that order is raised. d2y by dx square, it is raised to the power of 1. So hence it has a degree of 1. Degree is equal to 1, right? And in this case, suppose if it was del 2v by del t square is equal to, it is del time is equal to k times del v by del x whole square, right? Okay. So what is its order? Its order is 2, right? Okay. And what is its degree? It's, of course, it's 1, right? If it were 2 over here, it would be 2. If it was n, it would have been n, right? Okay. And suppose I say over here it's square, then its degree will be 2, right? Remember this thing, okay? So having discussed all this, we will move further, right? Okay. Now we are going to see linear differential equation. What is a linear differential equation? Well, a differential equation consisting of the degree 1 only, right? Okay. Suppose d2y by dx square plus dy by dx plus x is equal to 0. This is a linear differential equation, right? But there's a catch. There's one more condition, that if I use a variable, a dependent variable with any of the derivative term, or if I multiply suppose d2y by dx square dot dy by dx plus y is equal to 0, then this is not, due to this term, this will not be a linear differential equation. Why? Because you can't multiply derivative terms, right? In that, and in this case also you can't multiply by a dependent variable with this. Okay, we will see later that why is it the case, but for now this is the condition, that the first condition is that the every dependent and every derivative has a degree 1, right? And the second condition is that no products of dependent variable and derivative occur, right? Derivative occur. This is the condition, right? Of course, here there was product, so it is not a linear differential equation. But d2y by dx square plus y dy by dx plus y plus x is equal to 0 is a linear differential equation, right? So you need to understand this, okay? Let me raise this and then we are going to move further, right? Okay. Now what is meant by the solution of differential equation? So let's assume a very simple differential equation that y is equal to d2y by dx square or dx2, whatever you want to say. Okay. So what does it mean first of all? If suppose y is equal to fx is a function, right? Okay. You take the first derivative, it will be f dash of x, right? Okay. And if you take the second time derivative d2y by dx square, it is nothing but d by dx of dy by dx, right? Which is equal to f double prime x, right? You can say this, right? And of course that suppose y is equal to e to the power, not e, let's take a simple example, x square, right? So what is dy by dx? It's equal to 2x, right? Okay. And what is d2y by x? It is equal to 2. What is d3y by x square x cube is equal to 0, since the derivative of 2 is equal to 0 and derivative of x is equal to 1, right? Okay. So having said all this, let's see that what do we mean by the solution of a differential equation. Well, let's see. So in this case, that y is equal to d2y by dx square, we can see that y is equal to e to the power x is working in this case. Why? Because dy by dx is e to the power x, and if you again take the derivative, is equal to e to the power x, which is equal to y. So e to the power x is indeed a solution of this equation, right? So this is how we solve the differential equation. I mean, how we check that what is meant by solution. There are many ways to check to find the solution of the differential equation, which we are going to see in the later part of the video. So kindly bear with that. And of course, if you are liking this video, then please do like, subscribe my channel, and please do subscribe my channel, and please share it to everyone as much as you can. And now we will see that yeah, there's one more thing which I need to tell, that when we will solve the differential equation, let's see, first of all, let's see with the question. Suppose xy is equal to a e to the power x plus b e to the negative x plus x square. So we need to solve, we need to form a differential equation of this out of this equation. So here a and b are arbitrary constant which we can choose, right? Okay. So the thing you have to note that the order of differential equation is equal to the number of arbitrary constants present, right? Which means in this case there are two arbitrary constants, so at max you can take d2y by dx square, not more than this. Okay, so you have to remember this. You can't take d3y by dx cube, right? You can't take this. You can just take the maximum power, I mean the maximum order as 2, right? Okay, so we can solve this very easily, that xy is equal to a e to the power x plus b e to the power negative x plus x square. So we can simply take the derivative. We get y plus x dy by dx is equal to a e to the power x minus b e to the power negative x plus 2x. We can take another times the derivative and we get dy by dx plus dy by dx plus x d2y by dx square is equal to a e to the power negative a e to the power x, sorry, plus b e to the power negative x plus 2, right? So we have this equation. Of course we can further simplify it also. We will get 2 dy by dx plus x d2y by dx square is equal to a e x plus b e negative x plus 2, right? We get this thing, okay? And of course if you see that this can be said as, if you can see from here, that this is equal to, if you simplify you get xy minus x square plus 2, right? From this, okay, you get this value, the value of this expression as xy minus x square, and to add a 2 you added a 2. So this is your differential equation, 2 dy by dx plus x d2y by dx square is equal to xy minus x square plus 2, right? Okay, this is how you manipulate the things and you understand and solve the problems, right? And now let's see that how does a general differential equation look, okay? And of course you need to remember this thing also, right? Okay, and now let's see, okay? So any linear differential equation can be written as the function of the variable, independent variable, then the dependent variable, then the derivative, the first derivative, then the second derivative, until the nth derivative, right? Okay. Of course, for example, x plus dy by dx is equal to y. This is also the of its form, right? So basically, if you solve this, I mean, if you when you solve this, you get two kinds of solution. One is the general solution, and the one is the particular solution, right? Let me change the chalk. So what do I mean by the general solution? It means it will consist of n variables, right? Okay. And in the case of particular solution, you assign you assign values to the variables, right? To the arbitrary variables, right? I mean arbitrary constants, right? And of course the values you can't just do like that. It is like you have to solve for them, right? And this is how we distinguish between a particular solution and a general solution, right? And we will see it in the later part, okay? So don't worry about anything, okay? So what next we have to do? And okay, so we can take an example also. For example, that dy by dx whole square is equal to 4y. So you can take square root both sides. You get dy by dx is equal to plus minus 2 root y. So you get 1 upon 2 root y, 1 upon root y dx is equal to plus minus 2 dx. You simply take the integral. You get root 2 root y is equal to plus minus 2 x plus an arbitrary constant, right? Okay. So you get basically root y is equal to plus minus x plus c by 2. C by 2 you can write another constant, suppose c dash, right? So you get y is equal to c dash minus plus minus x whole square, right? Okay, so this can be one of the equations. So if you take one, so this is a family of curves actually which you are getting. And if you substitute, suppose we take y is equal to 1 plus x whole square, I mean c plus x, and you put c is equal to 1, right? If you are given at a point, suppose it satisfies a point, okay, and you get the value as c is equal to 1, so y is equal to 1 plus x whole square is a particular solution of this general differential equation, right? Okay, so let's move further, okay? Now we need to know one thing more, which I am going to tell. Just let me erase it. That when we are solving the solution, it can be written in two forms, right? What are those forms? We are going to see in just a minute. Okay. Just let me erase this, and yeah. So the solution can be explicit and implicit, right? Okay. It can be explicit and it can be implicit. What do I mean by explicit? In this case, the variables, or you can say that y is equal to some function of x. You get something like this. Suppose y is equal to x square plus x plus 2, right? And in this case, you get fx comma y is equal to 0. Basically, it is a two variable function. And suppose x square y plus z plus x sine y is equal to 0, right? This is how, suppose here also some other term, maybe cos x, right? So this is a implicit differential equation and this is an explicit differential equation. Of course, you can convert a explicit into implicit, okay? But it is difficult to convert implicit to explicit, right? Okay. So now let's see what next we have to do, okay? So let's see how we solve the first order differential equations of first order and first degree. Okay. Of course, we'll be dealing with only first degree only in most of the cases. So let's see. Okay. So solution of first order, first degree differential equation, right? So we are going to see this now, and the first one is, and I hope that you all must have studied in your 12th grade also, but still I will be telling from a very down level so that everyone can understand. Okay. So first is this variable separable method, right? Variable separable method. Okay. I hope my spelling is fine. Whatever. Even if it's not understand. Okay. Even if it's not can't understand it. Okay. So suppose you are given dy by dx is equal to e to the power x minus 2y plus x square e to the power negative 2y, right? So of course you can see you can separate the variables. How? Let's see. Dy by dx is equal to e to the power x into e to the power negative 2y. You know the property of e to the power alpha plus beta is e to the power alpha dot e to the power beta, right? This is simple property, you know, na? Okay. Be it plus or minus. Okay. If it is, then it is plus minus over here. Okay. It's okay. Plus x square e to the power negative 2y, and you can take e to the power negative 2y as common. When you take common, you get e to the power negative 2y into x square plus e to the power x plus x square, right? You get this thing. So you get dy by dx is equal to e to the power negative 2y into e to the power e to the power x plus x square, right? So you get e to the power 2y dy is equal to x e to the power x plus x square dx. You integrate it and you will put an arbitrary constant of integration. It is e to the power 2y by 2 is equal to e to the power x plus x cube by 3 plus c, right? This is how you solve using variable separable method, right? Now maybe my answer is wrong because there might be some calculation error at any point, so kindly neglect that. And yeah, now let's move further. Basically I'm trying to tell the concepts of the differential equations so that you all can understand things. Maybe if I make some calculation error, kindly rectify it on your own, okay? And if I see, I will write in the comment section if I see it later, okay? Or I will put it somewhere over here also, okay? So basically now we are seeing equation variable separable, or let me write equations reducible to variable separable, right? Okay. Suppose you are having dy by dx is equal to some function ax plus by plus c, right? So in this, how you convert it to variable separable? Let's see. You will do ax plus by plus c. You set it equal to t, right? And if you are having problem in understanding using this, you can see it using dy by dx is equal to 2x plus y plus 3 whole square, right? Over here you will do 2x plus y plus 3 is equal to t, right? And then solve. So I am telling the general approach, you all try using this, okay? So we get dt is equal to a dx plus b dy, and so we have dt by dx is equal to a plus b dy by dx, right? Of course it's fine. Okay, so from this we get dt by dx minus a into 1 upon b is equal to dy by dx. So we get 1 upon b into dt by dx minus a is equal to f at t, right? Is it fine? And now it is variable separable, right? Oh, I was checking my mic is working or not. So we can solve it. Dt by dx minus a is equal to b times f at t, right? So you get dt by dx is equal to b f t plus a. So now what you can do is you will write dt by a plus b f t is equal to dx. You simply integrate it, you will get the answer, right? If I'm correct, right? Yeah, whatever be the case. And over here also you get dt is equal to 2, dt by dx is equal to 2 plus dy by dx. So you substitute over here, you get dt by dx minus 2 is equal to t square. So you get dt by upon t square plus 2 is equal to dx, and you integrate it, and it's your job after that, okay? It is simple integral, right? So yeah, let's see further that what we need to do. And let's see. So suppose if you are given a question that sec x plus y is equal to dy by dx, right? You can do it as your homework. Of course, the method is same. I had chosen a general function. So if in this case the function is equal to sec x, right? Okay. Now let's see another form. Now we are going to see homogeneous equations, right? Okay. So how do we first of all check that whether the given function is a homogeneous function or not? So in that case, suppose it is like this: f of x comma y, it is given like this. What you do when you substitute phi of t x comma t y, where t is some variable, if you get t to the power n as common and then you get phi x comma y, then we say that the given function is a homogeneous function, right? And we won't discuss what is n over here right now, but you need to understand this, okay? So suppose if you are given this, let's see with an example so it will be better to understand. Suppose you are given dy, basically the equations of the form dy by dx is equal to f of y by x, right? Okay, understood? Then in that case, what you will do is you will use y by x as t. So you get the differential as dy by dx is equal to x dt by dx plus t, right? You substitute it over here, you get x dt by dx plus t is equal to f at t, right? You get this, and so you get dt by dx is equal to f at t minus t, which means that when you solve it further, you get dt by f at t minus t is equal to the integral dx plus c. Write this, you can solve it, okay? Yeah. If you want to solve, you can take an example that x cube plus 3xy square dx plus y cube plus 3x square y into dy is equal to 0. So when you solve, you get negative dy by dx is equal to x cube plus 3xy square upon y cube plus 3x square y. How do you check that is it a homogeneous function or not? You substitute x with tx and y with ty. Of course, this t and this t is different, right? This is another variable you can assume. Okay, so you get t cube x cube plus 3tx plus 3t square y by this stuff. And if you will see, when you take common, you get t to the power 0 into phi again, right? It means it is your homogeneous function, right? So to solve this, you have to make it to the form of y by x. So what you are going to do, you will do like this. You take x cube common from the numerator, you get 1 plus 3 into y by x, right, whole square, upon you take x square, you can take x cube as common from the numerator, I mean, whole cube plus 3y by x. Now it is just a function of y by x, and just apply this. Okay, I mean this method completely. You can assume y by x as t and then solve it further. Okay, now we will see another method, I mean another problem, that equations which are reducible to homogeneous functions, right? Homogeneous differential equation, I mean. Okay, let's see. Okay, so equations, is it fourth or fifth? I guess it is fourth. Equation reducible to homogeneous differential equation, right? Now we are going to see equations which are reducible to the homogeneous equation, homogeneous differential equation. Suppose dy by dx, we will take a case, is equal to a1x plus b1y plus c1 by a2x plus b2y plus c2, right? And over here a1 is not equal to b1, a1 by a2 is not equal to b1 by b2. Okay, so in such case, what you do is you substitute x as x plus h and y as y plus some k. So you get dx is still equal to dx and dy is still equal to dy, right? Which means dy by capital Dx is equal to a1x plus h plus b1y plus h plus c1 c plus I mean k upon the quantity a2 x plus h plus b2 y plus k plus c2, which is equal to, if you solve it, you get a1x plus b1y, a2x over here, 8 plus b2y plus a1h plus b1k plus c1 by plus a1h, I mean a2h plus b2k plus c2. And from these two equations, a1h plus b1k plus c1 is equal to 0 and a2h plus b2k plus c2. You know the values of c1 and c2? You know the value of a1, a2, you know the value of b1, b2. From this, you will solve for h comma k and you choose such h and k, right? Okay. You can take an example also, x plus 2y minus 3 by 2x plus 3 plus y plus minus 3 is equal to dy by dx. Over here a is equal to 1, a1 is equal to 1, b1 is equal to 2 and c1 is equal to negative 3, and a2 is equal to b1, b2 is equal to 1 and c2 is equal to negative 3. Okay, so from that you can solve for h and k, right? And of course when you solve this, you will get some function in capital X comma y, you have to substitute back to small x minus h, right? Okay, I will understanding this. And now we are coming to the exact differential equation. It is something really interesting. So we will see that. So now we are going to see how do we solve the exact differential equation. And it is simple, but it has some ideas which are like very interesting. So to solve for the differential equation, for the exact differential equation, suppose you have a differential equation m x comma y, where m is a function which is a m is a function of x comma y into dx plus n, which is a function of x comma y again to dy is equal to 0. And this is a general equation, right? Okay. So if m comma n are the functions of x comma y, then and this is equal to 0, then it is called an exact differential equation if del m by del y, right, is equal to del n by del x. This is your first condition, and of course it is basically the necessary and sufficient condition. So there's nothing much needed more. Okay, let me see if anything has to be done. But why is it so? Well, let's see. We'll see the proof also. That suppose we are given that m x comma y dx plus n x comma y dy. This is your equation, right? And suppose now what we are going to do is that in this we will assume a function over here that uh, suppose we get a solution of this as f of x comma y, right? So we have d of f x comma y is equal to del f by dx plus, I mean, del f by del x into dx plus del f by del y into dy, right? Where f is the function which is the solution of this differential equation, right? So let me see what we need to do. Yeah. Now we know that this equation, right? When you take the derivative, you will get back this equation, right? So it will be equal to, since it was a solution, if you take the derivative, you will get this equation back. It is obvious, right? So you get this is equal to m dx plus n dy, right? Is it fine? Okay. So what basically it means that m is equal to del f by del x. If we compare the coefficients, and we get n is equal to del f by del y. If we compare these coefficients, right? I mean the derivative terms, and you take again the derivative, you get del m by del y is equal to del 2f by del x into del y, I guess. Okay, if I'm not wrong, of course, since we are going, yeah, it is like this. And del n by del x is equal to del f by del x into del y. And now if we are assuming that f to be a continuous function up to the second order partial derivative, and of course which it is, right, then it means that del m by del y is equal to del n by del x if we assume f to be uh, continuous up to second partial derivative, second order partial derivative. Okay, so now we can say that m dx plus n dy is equal to df, right? And it should be equal to 0, which means that df is equal to 0, right? This is also the case. Okay, so now what we are going to do is we will see some problems and then we will see how we will solve it. Okay, let me erase this, and let's see how we solve such kind of problems. No need to worry much about it. I know that it must be confusing, so no need to worry. I will tell how to solve and you will understand it. Okay? So first of all, let's see the question. It states that we have to solve x square minus 4xy minus 2y square dx plus y square minus 4xy minus 2x square dy is equal to 0. So term with x, dx is m, and with y is called n, right? We have this To check for the exact differential equation, we will check del m by del y, which is equal to del by del y of the quantity x square minus 4xy minus 2y square, which is equal to minus 4x minus 4y. And if you take del n by del x, it is equal to del by del x of the quantity y square minus 4xy minus 2x square, which is equal to negative 4x minus 4y. So these two are equal, right? So the condition is satisfied. So it is an exact differential equation. And now we are going to solve this one. Okay. So let me raise this, then I will tell you how to solve it. We checked that it is so. Now we know that m is equal to del f by del x, which is equal to x square minus 4xy minus 2y square. And similarly, del f by del y is equal to y square minus 4xy minus 2x square, right? You are getting this thing. And now you can solve it, right? So if you solve, you will get f is equal to integral of x square minus 4xy minus 2y square dx. Just integrate it. You get f is equal to x cube by 3 minus 4x square, 2x square y plus minus 2xy square plus a constant. And this constant is assumed to be a function of y, right? In this case, it is just assumed. We will see how, okay? And now what we are going to do is we will substitute the value of this thing over here. You get del by del y. What is f? F is equal to x cube by 3. X cube by 3 minus 2x square. This square, let me write it clearly. X square uh, into y minus 2xy square plus c of y, right? And this is equal to this quantity y square minus 4xy minus 2x square. And now we can solve it. And when you take the derivative, this term will become 0 and you get minus 2x square minus 4yx plus dc by dy is equal to y square minus 4x y minus 2x square. So this and this gets cancelled, this and this gets cancelled. So you are left with that dc by c by dy is equal to y square, right? Is it the case? So you can solve that c is equal to y cube by 3 plus some other constant alpha, right? Where alpha is an arbitrary constant, okay? So now we have the value of c. So from this we can find the value of f as x cube by 3 minus 2x square y minus 2xy square plus y cube by 3 plus some constant alpha, right? And this is the solution of the differential equation, right? Okay, this is very simple, right? And most of the cases you can use this method, right? There's a trick also that you take m dx, you integrate it, then you take the terms which are not x over here and you integrate that. That is also a method, but I don't believe in that much because it is like you don't you move away from the concepts, right? So if you want, I will tell in the later part of the video or maybe in some other video when I make the probable questions or practice problems, then in that case I will tell. But for now I'm not telling that because else you will start focusing on that, okay? That is why I'm skipping that thing. And of course that is an option to avail or not. So if you want, I can tell in the later videos, but not in this one because it will be like more sort of rote learning things, which I don't want. Let me raise this and now let's see that what else can we do. Let me see, do we have another problem or can we do it by another approach? Okay, now we are going to see reducible to exact form. Sorry for my writing. Okay, so suppose in the case of m dx plus n dy is equal to, so in the case of m dx plus n dy, if del m by del x is, del m by del y is not equal to del n by del x, then in that case it might be possible that the equation is not exact, or there's another chance that it can be convertible or reducible to the exact form, right? So we'll see that only. Okay, so if del m by del y is not equal to del n by del x, so how do we check it? Well, we multiply by an integrating factor of I x comma y. Okay, so what we get from this, we get I x, let me, you know this, it is a function, so I m dx plus I m dy is equal to 0. Now del by del y of I m you will take, it is equal to m di by d del y plus m, I mean I del m by del y, right? Similarly, I del n by, so it is a chance that they both can be equal, right? If they are equal, then you are good to go, right? So how we will check it, that is another thing to be noticed. But before that, let me tell you a small concept that suppose you need to remember that sometimes you can guess the value of I using, you know, dxy, you know, dy by x, you know, d, do you know dx by y, and then you should know d ln y by x, and d ln x by y, 6 d tan inverse y by x. Of course, it is optional, you can calculate I, but sometimes it works in general sense, you can guess it using this. So if you want, you can do, but I won't prefer it, right? But it is taught many times, so that is why I'm telling you all, right? And you should remember d ln xy y dx plus x dy by xy, and similarly solve for all other. Suppose it is equal to x dy plus y dx, and suppose this is equal to, you can solve it, I've already solved, so that is why I'm not solving it, else it will take lots of time. So x dy minus y dx by xy, like this. Okay, so you can solve it, you should solve it actually, all of them, and you should write them in your copy if you want to guess the integrating factor. But it is more better to solve it, which we will see how we will solve. For example, let me tell you using a question that y into y square plus 1 dx plus x y square minus 1 dy is equal to 0. So notice here del m by del y is not equal to del n by del x, right? So in this case, what you're going to do is that if you solve, you get y cube plus y dx plus x y square minus x dy is equal to 0. So what you are going to do is you get y cube plus y dx minus x dy plus x y square is equal to 0. And notice that you have this term y dx minus this term. So notice that this, what is equal, this is equal to what, this is equal to y dx minus y minus x dy by x square, right? You know this thing, and this is equal to, sorry, it is x by y, and this is x by y over here. So it is equal to y dx minus x dy by y square, right? Is it fine? And it will be equal to x dy minus this. Okay, I'm not calculating, so there might be chance that I've written wrong only, and which I'm writing. So just notice that if it is wrong, just tell me in the comment section. Else, it is your homework to solve all this and write in your copy or whatever you want. If you can remember, it's good. If you can't remember, then also it's good. So we will calculate it. Okay. So no need to worry about anything. So over here we will divide by, since we see a y dx, so we will divide by y square. So you get y plus y dx minus x dy by y square plus x is equal to 0, which means that uh, sorry, it will be a dx also. I forgot to write that. It will be equal to dx over here, and it will be dy over here. Okay, sorry, dy and dx, right? So you get y dx dy plus d by x by y, right? Plus x dx is equal to 0. You integrate, you get y square by 2 plus x by y plus x square by 2 is equal to some arbitrary constants. Okay, and this is how you solve this equation, right? And right, okay. I hope I made a mistake over here. Yeah, yeah, sorry. It will be dy over here, and this is dx. Sorry. This is this. I'm really sorry. I'm really sorry. This is y, and this is your x. Okay. Let me erase this. You get y dx plus x dy. I'm really sorry for that mistake. Plus dx by y. And notice that this is d of xy plus d of x comma y, x by y, which means xy plus y plus x by y is equal to c. This is your result. Are you understanding this? How we got this? Okay. So now let's see the general method, how we solve for it actually. I'm sorry for that mistake again. Let me erase all this stuff. Okay. Now what we are going to do next is yeah. So we had calculated that uh, let's del I m by del y, it must be equal to del I n by del x, right? Is it the case? And this is a partial differential equation. If you can see, it is a partial differential equation, right? So let's see. So if we assume I to be a function only of x, right? So in that case, you can bring I outside, you get I del m by del y is equal to, and then you can solve for this, I del n by del x plus n del I by del x. You will get this thing, okay? And from this, you can calculate the value of del I by del x, which is equal to I del m by del x minus I del n by del x upon n, right? Simple. And now we can see that this is equal to I times del m by del x minus I mean this is del y, sorry, this is del y minus del n by del x by n. This is your thing, okay? And this will be a function of x, okay? So what we can do is that it will be equal to, which means that del I by del x is equal to I times some function of x, right? So you get I is equal to e to the power integral fx dx, right? And of course you can check for y also. In that case, this is simply mi times my minus nx by n, right? This is the case, okay? How I got this? I got di by I is equal to fx dx, integrate, neglect the constant, you get ln I is equal to fx dx integral raised to the power e, you get this thing, okay? I've been understanding this. And now if you don't understand this, let's solve it using a problem, so it will be very easy to understand, okay? So let's see it using a question that how the things are going actually, and we will see that how it will be working. Okay, so suppose the question is x square plus y square plus x dx is equal to plus xy dy is equal to 0, right? Of course, if you check originally, this is not of the form. It is not exact. It is not in the exact form. I mean, okay. You can check also. If you take del m by del y, you will get 2y, and if you take over here, you will get. Of course, they are not equal. It will be y and it will be 2y, so they are not equal. So you have to multiply by an integrating factor. So what you will get is that integrating factor over here, if you take 1 upon nx minus, sorry, my minus nx is equal to 1 upon x. If you solve this, just solve it. How? D, it will be equal to 2y, right? This is 2y and this is equal to y. So 2y minus y is y upon y x. Y and y gets cancelled, you get x, 1 upon x. So how did I knew that I have to take this only? Because if I took ny, like if I would have solved for y, then it would have been a different case. In that I would have got nx minus my by m, right, as the function. So in that case, what will I get? I will get negative y upon what is m? M is x square plus y square plus x. So you have to remember that you have to choose like that you have to take my minus ny or nx minus my, so that you get a function of one variable only. That is why I said that time that it is a function of x. Then only we can solve it, else we can't. Okay. So we have the value of the function fx. So now we have integrating factor is equal to e to the integral 1 upon x dx, and it is equal to x simply, right? If you can understand. So just multiply both sides by x, you get x square plus y square plus x dx plus x square y dy is equal to 0. And now it is a differential equation. It is an exact differential equation, right? So now you know how to solve this equation, right? Very simple, very easy, right? Now let's see linear differential equation of, okay, of first order. Yeah. Now we are going to see the linear differential equation, that how do we solve this, and let's see how it goes. First order. Of course, we are dealing with the degree one, so it's fine. So, so dy by dx plus py is equal to, uh, or you can say px into y is equal to q of x. So it is linear in y, and what is meant by linear in x? Dx by dy plus p of y into x is equal to q of y, right? This is the linear in y, and this is the linear in x, okay? But this is the linear in x and this is linear in y, okay? Sorry, I'm very sorry. So how do we solve this? Well, again, in this case, we can multiply both sides by dx and all, and if you see, you get dy plus px y minus qx into dx is equal to 0. And again, if you solve for the integrating factor, in this case it will come out to be e to the power p dx. Okay, over here m is equal to 1, so in that case del m by del y is equal to 0, of course. And over here, when you solve this, you will get your answer. Okay, so it is simple. If you want, you can do it. Okay, so you can take nx and ny. Yeah, it will work. Okay, so now let's see what else can we do. uh, Sorry, over here n is equal to, sorry, n is equal to 1, right? M is equal to this term, m is equal to this, the term with the dx is called m, right? So m is this term and n is this term, so del m by del y will be equal to p. So we got e to the power integral p dx, right? Okay, I'm sorry for that. If I make some mistake while speaking, please neglect that and try to manipulate things on your own also, because it's like it's one shot, so there are chances that I make some mistakes because it is in one go. There's no pause between it, so that is why. Okay, kindly bear with it. So of course you can solve like this. Okay, so you get, and what is the solution? Solution will be equal to y into integrating factor is equal to the integral q of x into the integrating factor dx, right? You get this, and of course an arbitrary constant. And in this case also you will get the same thing. Okay, just over there we will get x into integrating factor is equal to q of integrating factor dy plus c, and integrating factor in this case will be equal to e to the power p dx, right? This is how the things goes. Okay, and you can work on things, and yeah, it will work. Now equation that is reducible to the linear form, we will see that also, and let's see how it will work. Okay, so let me erase this, then we will see. Okay, so now let's see equation reducible to linear differential equation. Suppose f dash of y dy by dx plus p f of y is q of x, right? So you can assume f of y as t, right? Fine. So you get dt is equal to dfy, and with respect to x, we get, okay. Now what is it? It is equal to f dash of y, and by the chain rule, it will be dy by dx also. It is equal to dy by dx, right? So we get dt by dx plus p t is equal to q, and now it is a linear differential equation, and which you can solve very easily, right? Very simple, very simple. Okay, and now we don't need to see much on it. Bernoulli's theorem, I mean Bernoulli's equation, dy by dx plus py is equal to q by n y to the power n dy by dx plus p to the power y n minus 1 is equal to q, y to the power n minus 1 is equal to x. So we have dx is equal to, I mean, is equal to t. So we have dt is equal to n minus 1 to the power, if you, it is 1 minus n, sorry. You get y to the power negative n dy by dx. You bring over here 1 n minus 1. You get over here. So we have 1 upon n minus 1 into the quantity, it is 1 minus n, sorry, 1 minus n, 1 minus n into dt by dx plus pt is equal to q. Again, it's like that. Okay, simple. So this is how you get to solve this kind of problem. And now we are going to see solvable for p. What does it mean? We will see. Okay, no need to worry. Let me show you all how it goes. So we are going to see equation solvable for p. Solvable for p. What does p mean? P over here is dy by dx. Okay, remember this. Okay. Now see, it is, suppose question is dy by dx square minus dy by dx minus 6 is equal to 0. So you substitute p square minus p minus 6 is equal to 0. So which means p is equal to negative 2. I mean, you can factor as p minus 2, p plus 2, p minus 3 is equal to 0. So you get p is equal to negative 2 or p is equal to 3. So you get dy by dx is equal to negative 2. You get negative 2. So you get y is equal to minus 2x plus c1, and you get y is equal to, if you substitute over here, you get 3x plus c2. So you can combine the result, you get 3x plus c2 into negative 2x plus c1 is like the equation, the solution is equal to 0, somewhat like that. Okay. uh, y minus this, y minus this is the solution. Okay, you can say like that. Now we are going to see the equation solver for y. This is how you solve for y. Okay, I mean for p. P is just the differential term. Okay. Now let's see for y also. How do we solve for y in such cases? Solve for y, then we'll see for x, and then we'll move further. Okay. Solvable for y. So in this we have to note that the power or degree should be equal to 1 of y, right? Suppose the question is y is equal to y minus 2px plus xp square is equal to 0, right? We have this thing, and of course p is equal to where dy by dx. We are given this thing, okay? So how we will solve this? We will do 2px minus xp square. We will get this thing. Just differentiate y with respect to x. So we have dy by dx is equal to 2. What is the derivative of x is 1. 2p plus 2x dp by dx minus p square minus 2xp, I mean dp by dx, right? You will get this thing. And of course, what is this? This is equal to p. So we have p is equal to 2p plus 2x dp by dx minus p square minus 2x dp by dx. And of course, can you solve this equation? Well, let's see. Okay, let's see that how we are going to solve this expression. So you get, if you make it like this, p, it will be equal to p times 1 minus p plus 2x into dp by dx. 1 minus p is equal to 0. So you get 1 minus p into p plus 2x dp by dx is equal to 0. And you won't put this as equal to 0 since it don't have any differential term over there. So you will put only this one as equal to 0. So you get p plus 2x dp by dx is equal to 0, right? And can't you solve this equation? And if you solve this, you will get p is equal to root c by x. Of course, there will be plus minus, but for simplicity, I am assuming it to be plus only. Okay. So to solve for y, you will substitute this value over here. So y is equal to this thing. So when you solve this, you had y is equal to p 2px 2px minus xp square. You substitute the value of p, you will get the value as 2 root xc minus c, right? This is how you solve for y. Okay, this is solvable for y. Now we see for the solvable for x, right? Okay, I hope it's not going too fast, right? Of course, I have to cover it in less time, so that is why I am a bit fast. But I will make sure that you will understand everything, every possible concept over here, right? And please do subscribe my channel, and please like, share, subscribe my channel, and please share it as much as you can. And now we are going to further. Okay. So yeah, so now we are going to see for solver for x. We'll see it using a question. X is equal to p plus 1 upon t, right? Okay. Simply again you will do dx by dy is equal to dp by dx plus dp to the power negative 1 dx. And what's the derivative of t to d of the quantity x to the power n? It is equal to n x n minus 1. So it will be also equal to dp by dx, n will come outside, minus 1 into d 1 upon p square dp by dx, right? Are you understanding that? How is it going? It is very simple, right? Since it is by the chain rule, I have applied the chain rule. Okay. So, and what is, we know that p is equal to dx dy by dx. So we have dx by dy is equal to 1 upon p, right? Okay, which means that 1 upon p is equal to dp by dx p square minus 1 by p square. You can divide, multiply both sides by p, you get this thing. And I am sorry, I made a mistake over here. It will be dy dy. Sorry. dy over here, sorry. So it will be equal to, it's correct, this is dy. So we get dy is equal to p minus 1 upon p dp. So you get the value of y as p square by 2 minus ln p plus c, and this is the answer. Okay, this is how you solve for this is the solving for x. Okay, now we are moving to the other concept of the linear differential equation of higher order but of 1 degree of the first degree. Okay, so we'll see, let me resolve this. So now we are going to see linear differential equation of higher order with constant coefficients. So what is its general form? We can write it like this: d to the power n y, I mean dn by y dxn plus a1 dn minus 1 by dxn minus 1 y, and so on till an y x of x, right? This is your linear differential equation, and we'll see how to solve this one. Okay, a1 a2 till an are the constants, are arbitrary constants. So in this case the general solution is equal to the complementary function, complementary, I'm sorry if my spelling is wrong, complementary function plus particular integral. And how do we see all this? We will see in some time. So before all this, I have to tell one thing, that now we are going to use some operators. You know what is an operator? When you give some input, it will give some output, right? Okay. Suppose over here we will take d is equal to d by dx. It will take the derivative. Okay, it is the derivative operator in this case. So if you take the nth derivative, it will be like this. Okay, this is the operator, and you will apply this operator on a particular variable. Suppose d ny by dxn is equal to d ny, right? And this will be really helpful for our calculation purpose, right? Because we will be using auxiliary equations formed of d, right? So don't worry about those terms, we will see. Okay, so basically we will see first of all what is a complementary function, and then we will see the particular integral, and then we will solve it further. Okay, let me resolve this. So we are going to see complementary function. So what we are going to do in this is that we will take the original equation dny by dxn and a1 dn minus 1 y upon dxn minus 1 and minus 1 till a and y is equal to 0. I mean, earlier it was equal to x, but now we'll set it equal to 0, right? So it has become a homogeneous equation, right? Okay. So now what we are going to do is that we will solve this. We will get some solution out of it, and then we will, yeah, we will keep those solution for finding the general solution. Okay. And the particular integral, it states basically that you take a particular solution of this equation, and you do like this d and v, where v is the particular solution of the given differential equation dxn plus a1 dn minus 1 v by dxn minus 1, and so on till a and v is equal to 0, right? This is how you, is this is equal to x, sorry, in this case it will be equal to x. Okay, so here you convert it to homogeneous one. Okay, so now let's see that how we are going to solve. But before that, you have to remember that what is meant by linearly independent solutions. Suppose if y1 and y2 are two solutions of a equation of something, then y1 by y2, if it's not constant, then they're called, they're independent, then they are said they are linearly independent solutions, right? So which means, for example, y1 is equal to sin x and y2 is equal to cos x. Of course, they are linearly independent solutions, right? If they are not the constant multiple of each other, right? Okay. So let me see what else I need to teach right now. And you can also represent it using c1y1 plus c2y2 is equal to 0, right? And over here c1 is equal to 0 and c2 is also equal to 0. So for n solutions you can write c1y1 c2y2 till cnyn is equal to 0 and c1 is equal to c2 is equal to till is equal to cn is equal to 0, right? Okay, so this is what is meant by linearly independent solutions, right? But it is of course many times difficult to calculate these kind of variables, so these kind of constants. So we use something called Wronskian's determinant. And how we do it like that? How we do y1, y2 and till yn. Okay, if it's not equal to 0, then we say that they are linearly independent, right? Okay. And how we calculate this determinant? Let's see. Just a minute. Wronskian determinant. Okay. We need to see Wronskian determinant. So Wronskian determinant. W of y1, y2, y3, and so on till yn is given by this determinant y1, y1 dash, y2 dash, sorry, y1 dash, y1 triple dash, so on till y1 n minus 1th derivative, and y2, y3, and so on till yn, right? Similarly, y2 dash, y2 double dash, and so on till y2 n minus 1th dash, and similar is the case with this, and this one also yn n minus 1th derivative, right? This is how you calculate the Wronskian determinant, and if it is not equal to 0, then you say that the solutions are linearly independent, right? Okay. So now what we are going to do is that, yeah, let's take our complementary function equation now. What was that? Let me erase this, then we will discuss it. And I hope that you all are understanding whatever I'm teaching. And if you are not, then please to comment me in the comment section that where am I going wrong, so I will improve upon that thing. And of course no one is perfect, so maybe I'm also making many mistakes in this video, but please forgive me for that. Okay, so now we had dny by dxn plus a1 dn minus 1y by dxn minus 1 and so on till a and y is equal to 0, right? Okay. So we know this, and suppose that y1 is a solution and y2 is also a solution, a linearly independent solution. Linearly independent solution. Okay. This is just a short form which I'm using. Don't use this. Okay. So when we solve this, what we get? Yeah. So we substitute y. So we are dny1 by dxn so until a n y1 is equal to 0. And if you multiply by c1 to both equations, to this equation, it makes no difference, right? So you can make constant inside also, so you can write c1 like this also. It's okay? Yeah. And similarly dn y1 y2 c2 so on till a and c2 y2 is equal to 0. Just add these two equations, and what you're going to do from this? Well, let's see. If you add them, what you will get is that simply c1 times, suppose if I name this one as a, capital A, and this as capital B, so we have c1a plus c2b is also equal to 0. And if you know some of the algebra, you can say that d of c1 y1 plus c2 y2 by dx till an c1 y1 plus c2 y2 is equal to 0, right? If y1 and y2 are linearly independent in that case, right? That is why. So basically it means that if y1 and y2 are linearly independent solution, then it implies that c1 y1 plus c2 y2 is also a solution of this equation. And of course, if it would have been like n terms, then c1 y1 till cn yn would also be a solution of this differential equation, right? Okay, so where c1 and cn are like they are the arbitrary constant, this is called the general solution of this equation. Now we are going to see the solution of complementary function, which is a homogeneous equation, right? So let's see that how you solve it. Suppose you are given d2 by dx square plus a1 dy by dx plus a2y is equal to 0, suppose, right? What I told about the operators, d2y by dx square is equal to simply d, fine, and like that is equal to d2. So we get d2y plus a1 dy plus a2y is equal to 0, fine. Now just take y outside this expression. So we have d2 plus a1 plus a2 into y is equal to 0. I mean, this whole operator is being applied on this y, okay? So, okay, what next? Well, now it will be something illogical because we will be creating an auxiliary equation of it where we will replace m square plus a1m plus a2, where m is a number now, it is not an operator, m is a number, m is a variable, whereas d was an operator, right? Still, the way we factorize this, we can factorize this expression also. For example, d cube plus d square, I mean d square plus 2d plus 1 can be written as d plus 1 d plus 1, right? This is how you do like this, okay? So it is something really amazing that how the things are interrelatable, right? This is known as your auxiliary equation, okay? This is your auxiliary equation, and if you solve it, well, we will see. um, Suppose it has a root of alpha 1 and alpha 2, right? Suppose, so let me erase this and then let me tell further that what has to be done in this case. So we have m square plus a1m plus a2 is equal to m minus alpha 1 into m minus alpha 2, right? We have this. So we can write similarly this also. So we have d minus alpha 1 into d minus alpha 2 applied on y. So basically you are first applying this expression on y, then you will apply this on this complete, okay? So basically there's a first case to solve this equation, right? If alpha 1 is not equal to alpha 2, right? And alpha 1 and alpha 2 are real, right? Okay. So in that case, you can say d minus alpha 1 into d minus alpha 2 is equal to, or applied on y is equal to, suppose, okay? This is something which you will understand in some time. So you can say d minus alpha 1 y alpha 2 y, suppose it is equal to 0 in this case, okay? Suppose the first expression is only equal to 0. So you get dy by dx, I mean, let me write clearly. So this is a solution, dy minus alpha 2y is equal to 0, which means that dy by dx is equal to alpha 2y. So it means that dy by y is equal to e to the power alpha 2. So you get y is equal to, I mean, alpha 2 dx. So you get e to the power alpha 2, right? And similarly, we can say that d minus alpha 1 can also be equal to 0 applied on y. So from that you can get y is equal to e to the power alpha 1 also. So we get y is equal to e to the power alpha 1 and y is equal to e to the power alpha 2. And when you take the difference y1, y2, you get e to the power alpha 1 minus alpha 2, and which is not a constant, of course, right? So which means that from this you can say that y is equal to c1 e to the power alpha 1 plus c2 e to the power alpha 2 is a general solution. And for nth degree, if there are n solutions, you get y, the general solution is equal to c1 e to the power alpha 1 plus c2 e to the power alpha 2 and so on till cn e to the power alpha n, right? This is general solution for nth degree, for nth order one, right? Degree is one only, right? So this is for the case when alpha 1 is not equal to alpha 2 and alpha is a real value, right? But what happens if they both are equal? So in that case, what we are going to do? Well, let's see. Okay. So for the second case, when we are saying that they are equal, what we will do is that in the case alpha 1 is equal to alpha 2 and alpha comma beta are real or whatever, okay? Let me change the chalk. So alpha and what I have written this alpha is real, right? So in that case what we are going to do is that yeah, we can say that we can assume them as alpha. So d minus alpha applied on d minus alpha applied on y is equal to 0. We know this, okay? So now what we are going to do is that we will say d minus alpha applied on y is equal to z. Z is some other function, and we will apply this d minus alpha on that z, and that will be equal to 0. This is how we are going to solve this problem, right? Okay, now notice that d minus alpha means, I mean to say that d minus alpha is equal to d minus alpha applied on z is equal to 0 is similar to this case, right? This one, which means that z can be written as c1 e to the power suppose alpha x, right, where alpha is the value, right? So we can say that d minus alpha applied on y is equal to c1 e to the power alpha x, right? This one, okay, we substitute the value of z over here. Are you understanding it, right? So now you get dy by dx minus alpha y is equal to c1 e to the power alpha x. You will get this. And isn't it solvable? Let's see. Just a minute. So just observe that we have dy by dx is equal to c1 e to the power alpha x, or just leave it, plus minus alpha y is equal to c1 e to the power alpha x. We have this expression. Now notice that this is a linear differential equation, right? It is a LDE, right? It is very simple to solve. It is a linear in y, right? So you get integrating factor as e to the power negative alpha dx, you get e to the power negative alpha x, right? And the next thing which you get is that y times e to the power negative alpha x is equal to simply the integral c1, of course, it is c to the minus alpha x into c1 e to the power alpha x dx. You remember formula, right? That integrating y into integrating factor is equal to the integral q times the integrating factor into dx, right? This is the case. So you get y is equal to e to the power alpha x into the quantity c1 we can take common. So we get this and this gets cancelled. So we have cx, right? And this is it. So we get the value of y as x c1 x e to the power alpha x, right? So do you understand that how the things are going? And if there are and if alpha repeats r times, right, it has repeated for 2 times, right? In this case, if it repeats for r times, then in that case this is equal to c1 x to the power r minus 1 plus c2 x to the power r minus 2 and so on till cr e to the power alpha x, right? This is how. And of course you can solve it using, for example, d minus alpha, d minus alpha, d minus alpha. You can check for 3, then 4 and so on till n. You can check, okay? You get this result only, okay? Is it simple, right? Is it easy to understand? And of course it will be a constant over here also, so it will be basically equal to c1x plus c2 e to the power alpha x, right? Now it's correct, okay? So I hope you are understanding this. So now if we have the case of imaginary roots, then what is gonna happen? Let's see. Well, let's see. So now we see the case of imaginary roots. Imaginary roots, right? So suppose the roots are alpha plus I beta and alpha minus I beta. So what we are going to do is that we know that they both are independent. I mean, they both are different. They both don't have the same numerical value. So which means that it is the first case of different variables. I mean, what was that? With different values, right? They don't have same values. So it is like this. So we can apply the same concept that y is equal to c1 e to the power alpha plus I beta plus c2 e to the power alpha minus I beta, right? This is how you will write it like this. And of course c can be some imaginary number also now. That is why, okay? So now what we can do is we can bring e to the power alpha is common, e to the power alpha is common. So we have c1 bar e to the power I beta plus c2 bar e to the power negative I beta, and we know the relation that e to the power I theta is equal to cos theta plus I sin theta. So we can just apply this over here. So we get y is equal to e to the power alpha into the quantity. Uh, it will be alpha x, of course. This x also. So beta x, alpha x. So when you substitute this, you will get c1 plus c2 bar cos beta x plus I times c1 minus c2 bar sin beta x. Of course, it is a simple calculation. You have to just substitute beta x over here and negative beta x, and then you just add, you will get this result, okay? So what you get is that you can say this as c1 and this as c2. So you get the result as e to the power alpha x into the quantity c1 cos beta x plus c2 sin beta, including I also over here, beta x, right? This is how you solve in the case of imaginary, right? And now what we are going to do is that yeah, if alpha plus I beta and alpha minus I beta are repeated r times, right? They are repeated r times, right? So in that case, y is equal to e to the power alpha x p1 plus p2 x so until pr x to the power r minus 1 into cos beta x plus q1 till qr xr minus 1 into sine beta x, right? This is how you solve. And you can derive it using the first theorem also, that first problem, which we discussed when the roots are different and they are real in that case, okay? So basically, let's see what we need to do now. Suppose, let's see, we will understand complementary function using a question now. So it will be better for you to understand also. Let's see. So suppose the question states that, let me erase this, then we will see. Suppose the question is d2y by dx square minus 5dy by dx plus 6 is equal to 0. So you can write it like this: d2y by d2 minus 5 dy plus 6 is equal to 0, and you substitute m square and you take y common, you get d square minus 5d plus 6 plus, like, sorry, not 6 will be over here, y plus 6 is equal to 0. Is it correct? Yeah, is it? I guess there is some problem in the question. Yeah, it will be y over here then. Yeah, now it's fine. Y, yeah, now it's correct. There was some misprint in the question. So now you can substitute d as m to create an auxiliary equation. You will get m square minus 5m plus 6 is equal to 0. So you get m is equal to 2 comma 3. So of course you can write this as d minus 2 d minus 3 into y is equal to 0. Either you apply the complete procedure or you write y is equal to um, c1 e to the power 2x plus c2 e to the power 3x, and that is your complementary function in this case. Okay, this is how you solve the things, right? Is it correct? Yeah. And similarly you can apply for different cases also, right? It will be very similar. Okay, so let's see for the particular integral now. Okay, and don't worry, we will do questions in the last in one of the last videos of this semester, right? I guess in the April, no, not in April, maybe till the March end. Okay, so in that we will do a practice session. In that we will discuss all the tough questions, right? So no need to worry about this. This is videos for basically to improve your concepts and everything, right? It is not related much to the problems, right? To high level problems. Of course we are doing problems, but they are not that high, that much high, right? Okay, so of course if your concepts are clear, then everything is fine. If it is not, then there are problems even if I do hundreds of problems, right? That is the thing. Okay, so just focus on concepts right now, that what is going on, right? Okay, so now we are going to see integral particular integral, right? Okay, so what we had done, that we had fd into y is equal to x, right? Remember this, you had dny by dx n minus 1 plus a1 dn minus 1 y by d x n minus 1 and so on till a n y is equal to 0 is equal to x, sorry. So similar thing which we can do is you can dny plus a1 dn minus y and so on till a n y. So you can take y as common. So we have dn till a n y is equal to x, which means that function of d applied on y is equal to x, right? It is not the multiplication, it is the operator that is being applied on the variable y. Okay, so f of d which is being applied on y is equal to x. So particular integral is equal to 1 upon f of d applied on x, where f of d is just an inverse of this expression. For example, 1 upon f of d is inverse of what? Of this, of f of d. For example, if I said dy is equal to x, which means y is equal to 1 upon d applied on x, which means integral of x dx, right? I will mean this. Okay, this is like this. Okay, so let's see. Let me erase this, then we will see it using some problem. Then it will be better. Okay, so let me show you all. Suppose. Well, if you can write it in general form, f of d can be written as d minus alpha 1 into d minus alpha n and 2 till d minus alpha n. Can we write it like this? Of course, we can write it like this if it is a polynomial. If we are using the auxiliary equation of nth degree, then it can be written as like this. Okay, which means that We can say 1 upon d minus alpha 1 till d minus alpha n applied on x, right? So what we are going to do is that in this we will assume 1 upon d minus k, where k is between 1 and n, right? It can be 2, 3, 4, whatever, okay? Applied on x is equal to suppose t, so you get x is equal to dt minus dt by dx minus alpha k t, right? And whatever be the value of x, and of course it is linear in t, so you can evaluate it. It is very simple, okay? So if you try to solve, you will get the integrating factor is equal to e to the power this, and you will get e to the power negative alpha k x. So you get the solution as x, I mean t times e to the power negative alpha k x is equal to the quantity integral e to the power negative alpha k x into capital X dx. This capital X is a function. It is a function of small x, right? Okay. So get t is equal to e to the power alpha k x integral e to the negative alpha k x capital X dx. This is how you solve it, okay? And then you continuously apply the same thing, okay? I will understand in this, and of course there will be a constant plus some constant, right? So, but in the case of particular equation, we neglect this constant at 0, okay? So that is how you get the equation, right? Okay. So now let's see if we have a problem which we can solve right now. Let's see a simple one first of all, then we will see if we can do some higher level problems too. Let's see. So we are going to see a problem, then we will find its general solution, and then we will be almost done with our lecture. But we have to still see some one or two theorems, and then how to solve linear equations, I mean the ordinary differential equations simultaneously. We have to see that, but of course we won't do much questions related to that because we will see it in the last video in the practice session also. So that is why don't worry about it, just see the concepts, okay? Okay, so let's see the question. It states d square minus 3d plus 2 of the quantity y is equal to e to the power 3x. So we get y is equal to 1 upon d square minus 3d plus 2y, 3 to the power e to the power 3x, which is equal to 1 upon d minus 1 d minus 2 e to the power 3x, right? So what you're going to do is 1 upon d minus 2 e to the power 3x is equal to t, which means that e to the power 3x is equal to dt. Let me write it. D minus 2 applied on t. So we get e 3x is equal to dt minus 2t. 3x is equal to dt by dx minus 2t. From this, if you solve, you get t is equal to e to the power 3x by 2, and again you will do 1 minus 1 upon d minus 2 d minus 1, sorry, of e to the power 3x by 2, and when you apply you will get set it equal to u now, or you can use t also, there's no issue. 3x by 2 is equal to du by uh, dx minus u, and if you solve you will get the answer as the particular solution, means the solution as in this case as e to the power 3x by 2, right? From all this, final result is this only, okay? So let's see if something else we can do. So let's see if we have a general solution question, if we can try doing it. If we can see some solution, so of course we can certainly. So let's try to find the general solution of this equation only, okay? Let's see. So we have got the particular integral. We have got the particular integral as what? We have got it as e to the power pi is equal to e to the power 3x by 2. We have got this, okay? And now what we are going to do is that let me see if I have any questions, so it will be then better to see the things. Maybe I don't have right now any question like that. Well, no issue. Um, so this is a particular integral, and what is the complementary function of this? You can simply write d minus 1 into d minus 2 applied on y is equal to e to the power 3x, and of course here alpha 1 is equal to 1 and alpha 2 is equal to 2. So y is equal to, in this case, it is equal to c1 e to the power c1 e to the power, this is your function as it is, but you have to set it, so this is equal to 0, right? So e to the power alpha x plus c2 e to the power 2x. So we have the general solution as c1 e to the power x plus c2 e to the power 2x plus e to the power 3x by 2. This is your solution. You substitute it, it will work, right? If you want, you can check also. You can take the derivative test and it will work. You just substitute it over there, it will come equal to 3x, right? E to the power 3x. Okay, so this is how you solve this problem. And now let's see what else we need to do. um, Now let's see Cauchy Euler equation. Let's see how it goes. Okay, and then we'll see Clairaults theorem. Then we will see the solving of differential simultaneous differential equation, and then we will be done. Okay, so no need to worry about anything. It is very simple. Okay. So you remember that how I got the general solution? General solution was equal to the complementary function, whatever you get the result from complementary, then whatever result you get from the particular integral. And in particular integral, you don't have any constant because it is a particular solution. So in that case, you won't get any constant. Okay, that is why. So now let's see Cauchy Euler equation. Cauchy Euler equation, right? Okay. So a linear differential equation, a linear differential equation of the form xn dny by dxn plus a1 xn minus 1 dn minus 1 y by dxn minus 1, so until a n y is equal to x, right? And I hope that you are understanding this, and it is simple, just don't worry about it. And what does it mean is that the coefficients in this case is not a constant value, but they are dependent upon the variable x, right? So they are variable constants. So Cauchy Euler theorem is used to determine the solution in the case of variable constants. Okay, I mean variable, yeah, variable constants, whatever. So let's see, non-constant coefficients, variable coefficients, right? So in this case, we choose a function x is equal to e to the power z, where z is an independent variable, right? Uh, just, just a minute. Is independent variable. Okay. So you get z is equal to ln x. So you get dz by dx is equal to 1 upon x. So we have dy by dx is equal to dy by dz dot dz by dx, which is equal to 1 upon x dy by dz. So we have x dy by dx is equal to dy by dz. Do you know this is chain rule, right? This is chain rule, okay? If you remember that, okay? So you get this expression first of all, and when you take the second derivative, or you can write it like this also, that it is x d is equal to, suppose d by dx we are calling as d, and d by dz we are calling as d1. Okay, just for simplicity, let me use another chalk. So what we are going to get is that it is equal to d1y, right? This is how it goes. Okay, it is of course applied on y. Okay, so here xd is equal to d1 is an operator, right? Okay. Now you take the second derivative. What do you get? d2y by dx square, right? This is equal to, this is equal to uh, what was the expression? It was this, yeah. It was equal to d by dx of the quantity 1 upon x dy by dz. Okay, and if you solve this expression, you get negative 1 upon x square dy by dz plus 1 upon x, right, into d by dx of dy by dz, right? How we get this? Well, how we solve this? We will do dx dy by dz. So first of all, we are going to apply the chain rule, of course. So we, it will be d2y by dx square, I mean dz square into dz by dx, right? And what is dz by dx? It is equal to 1 upon x. So it is equal to negative 1 upon x square plus dy by dz plus 1 upon x square d2y by dz square, right? This is how you approach the things. So you get x square to d2y by dx square. This is equal to d2y by dz square minus dy by dz. So you get x square dy is equal to d1 square minus d1, which means that uh, d1y, which means that x square d is equivalent to d1 minus 1, right? This is d. Okay, this is how you get the function. This is d2, so this is d2. Okay, so let's generalize this expression and let's see that for nth degree what will be the expression. Let's see. So for the nth degree we will have x and d, and use a similar method. You will get d1 minus 1 into d2 minus 1, so until d and d, sorry, d1 minus 2, d1 minus n minus 1, right? This is how the things work, right? This is very easy to understand, right? Let me see it. Yeah, I have written correctly. So how will it help us? Let's see. Okay, so let's see it using an example that how it is going to help us. This substitution and this. Okay, so I have an example and we'll see. So let's see that example. It will be then clear. Suppose the question states that x square d minus xd plus 2 into y, right, is equal to x ln x, right? So here the constants are not indeed constant. These coefficients are non-constant, means they are variable. So basically this 2. Okay, so what is x square d2? It was equal to d1 into d1 minus 1, d1 minus 1. Okay, so we have d1 minus 1, and what we have xd, it is equal to d1, it is equal to d1, right? So what else we can do? We can just yeah, now we can substitute the value, and we have e to the power z is equal to y is equal to x, sorry. So we can write it like this: d1 minus 1 minus d1 plus 2 times, what is y? Well, over here y is equal to, well, let's write y as it is. And what is x? X is equal to e to the power z into z, right? So we have d1 square minus d1 minus d1 plus 2 into y is equal to e to the power z into z. So we have the quantity d1 square minus 2 d1 plus 2 y is equal to e to the power z. So we have the expression, and now notice that this is just the linear differential equation of higher order, right? And it is easy to simplify, right? You can see that over here you are going to have imaginary solutions, so you know how to solve it, and you know how to solve its particular solution, right? And of course, in the case of particular solution, it will be 1 upon d square minus 2d plus 2 times e to the power z into z, right? This is the case. But now you would be thinking that how to factorize this, then of course you can do d minus alpha minus 1 upon d1 minus alpha 2, where alpha can be imaginary number also. Who said that it has to be real only for partial fraction, right? Okay, I mean this has to be in multiplication, sorry, right? Do you understand it? Okay. Then apply it on f at z. Apply this on this, then apply this on this. Okay. There are tricks also, I mean some methods which we use generally, but I'm not discussing it right now. We will discuss in the problem session, right? So I hope that you understood that if it is in Cauchy Euler, you substitute x as e to the power z, then you make this changes depending upon the power, and then you make it look like the linear differential equation in higher order, and then you solve it. Okay, this is the general approach of the Cauchy Euler theorem. And now one thing which I need to tell is the Clairaults theorem. Let's see, where is it? Yeah, this is it. So what is the Clairaults theorem? Let's see. Let me erase this, then we will see it also. And then we will see the simultaneous ordinary differential equation. And I hope that much is the only syllabus. I don't think so that there is anything much more in it. Okay. So let me erase all this. So we have Clairaults equation. So if we have y is equal to px plus f at p, where p is equal to dy by dx, then the solution of this equation is you replace p with a constant c. It is an arbitrary constant. So y is equal to cx plus f at c. This is the solution of this equation. It is very simple, right? Just in a single step you can do. Okay. Just substitute it with the arbitrary constant c and you get the answer. This is the Clairaults equation. Okay. Okay. So I think we have done almost everything. Just the thing which is left is the simultaneous linear equation. I mean simultaneous differential equation, ordinary differential equation. Let's see that also how we will do. We will just see an idea, then we will solve the questions in the solving session. Okay. So let's see. Okay. Simultaneous ordinary differential equations. So simultaneous differential equation, in this case it is, suppose you have p1 dx plus q1 d y plus r1 dz is equal to 0, and p2 dx plus q2 dy plus r2 dz is equal to 0, and you are set to solve this differential equation simultaneously. So of course you can solve it using the cross multiplication method. If you remember that if ax plus by plus c is equal to 0 and dx plus ay plus f is equal to 0, then you solve it. Similar is the case in this also. So dx upon the determinant of this quantity, it will be q1 r2 minus q2 r2 r1, sorry, dy. You put a negative sign over here, but I'm neglecting the negative sign. It should be p1 r2 minus p2 r2 p2 r1, but due to negative sign it will be reversed. So we will get P2 R1 minus P1 R2 is equal to dz, the determinant P1 Q2 P1 Q2 minus P2 Q1, and we can write it as dx by capital P, this dy by capital Q, and dz by capital R, right? This is how it will look. And here P1, P2, Q1, Q2, R1, R2, P, Q, R, they are the function of x, y, and z. Okay, understood? Okay, so let's see it, understand it using a problem. It is, will be a very simple, right? Let's see. Let's see how we will solve this equation, this problem. This is ODE. So suppose a very simple problem, the simplest one, dx by 1 is equal to dy by 1 is equal to dz by 1. It is very simple, right? So in this case, you will equate these two, then these two. You don't need to equate the third equation, because the third one can be formed using these two equations only. Dx is equal to dy, which means that x minus y is equal to c1, and dy is equal to this one. Dy is equal to dz, which means that y minus z is equal to c2. So one can be dx is equal to dy dz, which means x minus z is equal to c3. But notice that if you subtract these two equations, if you add these two equations, x minus z is equal to c2 plus c1, which means that third equation was contained in these two equations only. So you just need to evaluate these two equations only. No need to evaluate the third one. Okay, are you understanding it? Okay. So now let's see another kind of problem. It is, we are doing just very simple right now, because we are doing the best problems in the problem solving sessions, right? So dx upon x, y, z, and of course it is your duty also to do the problems on your own also, right? It is useless even if I tell all the concepts and you don't practice anything, right? So you have to practice things, of course, but the thing is that don't stress yourself a lot about anything. Okay, life is just like that. Okay, it is like it should be stress free, of course. Whatever you are doing, it should not have any stress on yourself, because you are the priority. Okay, okay, just leave all that. So we have dy by y is equal to dz by z. Okay, no need to equate these three. Okay, so you can integrate. You get ln x by y is equal to ln some c. So we have x is equal to, in this case, y e to the power c1, and in this case y is equal to z e to the power c2, something like that. Of course this is also a constant, this is also a constant, e to the power c. So we can write x is equal to k1y and y is equal to k2y, k2z, sorry. Okay, now there are few methods which we use to solve this simultaneous equation. The first one is said solution by cancellation of variables or variable, right? Suppose d x y z is equal to dy by zx is equal to dz by xy, right? Equate these two, you get dx by yz is equal to dy by zx. So you cancel z and z, you get dx by y is equal to dy by x. So you get x square is equal to x dx is equal to y dy, and you, when you solve, you get x square minus y square is equal to a constant. Okay. And now when you equate these two, you get dy by zx is equal to dz by xy. So you cancel this, you get y dy is equal to z dz. You solve y square minus z square is equal to c2, c1, and this you can say c2. Now it is solvable. Okay. Now it is solved actually. Okay. So now the second is the use of one integral What is integral? Integral means solution. To find second, like particular integral, it was particular solution. Okay, understood? What is the meant by integral over here? So let's see the second one. I guess it must have been like 2 hours since I started. So the second is use of one integral. Integral, by integral I mean the solution of to find second equation. Okay. Suppose dx by 1 is equal to dy by 2 is equal to dz by 5z plus tan y minus 2x. Well, we can first of all solve this equation. You get dx by 1 is equal to dy by 2. So you get 2x minus y is equal to some constant c, or y minus 2x is again equal to some constant c. Okay, suppose this c dash. So notice that dx is equal to dz by 5z plus tan y minus 2x, right? So notice that y minus 2x is a constant. Okay. So we have dx is equal to dz by 5z plus tan c. So now we can simply integrate it since tan c is a constant now. Earlier it was a variable. Integrate, what do you get? X is equal to ln 5z plus tan c by 5 plus a constant c. You get the answer. Right? Simple? Easy? Okay. So suppose c double prime. Okay, we need another constant. Now we can use multipliers to solve this. Use of multipliers. What does it mean? Well, let's see. Use of multipliers such that the denominator of new fraction is 0. Okay. So if you remember ratio and proportion, in that it was suppose uh, x1 by x2 is equal to y1 by y2 is equal to y3 by y z3 by z1 by z2. Then it is equal to ax1 plus b y1 plus c z1 is 1 a x2 plus b x2 y2 plus c z2, right? If you remember this thing. Okay, similar we can apply in this case also, right? I have written correctly? Yeah. Similarly in this case also we can do the same thing. Just what we are going to do is that we will set we will choose a b and c such that ax1 ax2 plus bx2 plus cx2 is equal to 0, right? Let's see how it goes. Suppose dx by mz minus n y is equal to dy by n n x minus lz is equal to dz by l y minus mx. But what is meant by multiplier? Well, here b c is the multiplier. Okay, is the multiplier. Okay, multiplier level. So in this case you have to make the denominator equal to 0, right? So just see mz minus ny plus nx minus lz plus Ly minus mx is equal to 0, a, b, c. Now, what can be a, b and c? So that is where practice is required. So you just see that you have m over here and a z, and you have a m and a x. So what if it was a z over here and it was x over here? Okay, it will cancel. You have a ny, you have a l, you have a nx. So if it was z and then it was x and here it was y, it would cancel. It means that a comma b comma c is equal to x comma y comma z in this case, just by some manipulations. So it is equal to x dx plus y dy plus z dz, and of course when you solve this will be equal to 0 when you substitute x. You substitute x over here, you substitute y over here, you substitute z over here upon 0, and if you set it equal to suppose x dx plus y dy plus z dz by 0, of course since these are finite values, which means that to make it finite this expression must be equal to 0, right? Which means x dx plus y dy plus z dz is equal to 0. Just integrate it. You get x square plus y square plus z square is equal to some constant. And this is how you solve these equations. And of course, there's one more topic in which there's a fourth one also, use of multiplier such that denominator of the new fraction is not equal to 0, but that is something complex. So that is why I will not discuss it right now, since you will get confused. So whatever I've taught till now, just practice questions on it. And I hope that you all enjoyed this video, and if you really like this, then please do like, subscribe my channel, and bye bye, take care.